Alright guys, yeah, I know I haven't been on here for a while. I've had some health problems. I had some real bad kidney stones for like 3 weeks. I had like 6 kidney stones in 3 weeks, but I wanted to talk about Thomas Moray and the sea of energy in which the earth floats. And all the pictures are gone, but this is his book, The Sea of Energy, and here's the chapters. It's a really good read if you never read it before. You know, I do a lot of stuff. I build stuff and build hot rods and motorcycles and all kinds of things, you know, but I'm real big into electronics too, and I've been researching free energy stuff for, you know, well over a decade. That's really the reason I got into learning electronics, and now I can make pretty much anything I want if I had the time to do it. But you know, there's a lot of things I think about and want to experiment with, but I just don't have the time. And this is one of the things that I will eventually get to, and I've got many ideas about, and I think about a lot, but I'm not going to get to it fairly soon. So this is first off, this is Feynman Lectures, Caltech, EDU _09. If you search Feynman at atmospheric electricity, you'll find it. So this is a real simple concept here. I know not everybody's going to know all this stuff I'm talking about, so I'm going to try to keep it simple. Basically, there's static electricity everywhere around you. For every meter above the ground, every 3 feet above the ground, there's 100 volts. And then at 6 feet above the ground, there's 200 volts. You know, and it just keeps compounding all the way up to the atmosphere, which is super high voltage. So the problem with this, all this free energy that's just laying around everywhere, is you know, you're grounded, so it kind of arcs above you. But the big problem with this free energy, and the reason why people have so much trouble getting it, and see, I've got some ideas to get around all that, and I'm going to get to it, how to harvest this electricity in a real way, not these fake ways you see on YouTube where people don't know what they're talking about. Well, first off, you need to know, okay, yeah, there's 200 volts at your nose, you know, but how much current is there? I mean, we're talking about static electricity, basically just charged ions. So they're charged ions at rest, so they're static. They're at rest. I'm not sure where it's in here somewhere, but basically it says that there's only 10 picofarad or 10 picoamps. Top of the atmosphere is 400,000 volts, but there's only the density of this energy. You know, you got to think of it as in density. You know, how smushed together is it, or is it just spread out? You know, well, the density of this electricity is 10 picofarads per square meter, and a picofarad is a millionths, or not picofarads, picoamps. There's 10 picoamps per square meter, and that's a decimal point with 9, like about 12 zeros behind it before the 1. I mean, it's you know, a picoamp is a million amps. Sometimes it's even called microamp instead of a picoamp. So there's almost no current, right? So if you were to calculate, okay, say you're reaching 200 volts, right? And you're getting the full 10 picoamps. Well, and you want to know how many watts that is, how much power can be done with that. Well, you multiply watts by amps. So if you multiply 10 picoamps by 200 volts, you'll get like I don't know, whatever it is, but it's less than a microwatt. I mean, it's not enough to do any work at all. And what would really happen is, if you see, and the ground is just a vast source of negative electricity. So if you were to tap into this ground and make a ground, and then you'd put a wire up to this 200 volts, and you were trying to do some work with it, because of the resistance, the resistance means everything. The resistance is going to draw out current, and this static electricity doesn't have no current to give. So it's going to take this 200 volts and make it a zero, or like a very tiny fraction of a volt, because of the resistance. So there's a trick to get around to accumulating and using static electricity, and you've got to do it in such a way where you don't put resistance to it, because you want to keep that high voltage, because that gives you some leadway to mess around, but as soon as you go putting resistance to it, you'll knock that voltage down to nothing, because there's no current behind it. So look for this Feynman link. Just Google Feynman atmospheric electricity. This is a good read. It'll tell you what's all up, So I'm going to close. Well, I'll leave this open for now, but I'm going to go back to Thomas Moray. Now, I mean, if you don't know who Thomas Marais was, well, shit. I closed that link, I think. Thomas Moray made a free energy device that supposedly ran off of radiant energy, and he was able to create 50,000 watts of power. Here he is right here, or Tom Bearden website. Well, this is Thomas Moray right here with his energy device. There's his device, and basically what it is this. He's got his device, which is a bunch of vacuum tubes, because this was back in the 1930s, and he has this huge metal cable that runs across up in the air by quite a bit. This says 2.5 meters in the air, but actually this is wrong for sure, because I've seen it was 80 feet in the air. He had two telephone poles that were like 80 feet, or some trees or something, and he had a really good insulation between this basically an antenna and the poles that were holding it up, right? So because I mean, when you start talking about really high voltages, then you got to be really concerned about insulating everything, because the voltage will jump. So basically, you had this big wire up here, and one of the big questions is, because in Tesla's patent for radiant energy, he says to use a piece of metal that is covered in an insulator. So now, say you have this big cable from something, like a telephone pole cable with an insulator on it. Well, that's the same thing. So I mean, that's what he did. He had a big piece of cable. Now the big question is are you using this cable so you're connecting to the metal on the inside of the insulation and you're capping off the insulation everywhere else? So are you using this cable as half of a capacitor, and on the outside of the insulation, the air and all that charged ions are acting as the other half of the capacitor? That's the question, if that's what's happening or not. And I'm not sure if the air and the ions in it, charged ions in it, are acting as the other half of the capacitor, because you just got a piece of metal with insulation on it. Well, that's half of a capacitor pretty much. So that's a big question. I still don't know. It would take some testing. And yeah, he made power from this big antenna outside in this box with some vacuum tubes in it. And he was a smart dude, you know, but it was pretty early. It was in the 1930s. So this right here, if you look, I'll link all this stuff in the description, but this, you get started here. This is the Sea of Energy. It's a book he wrote. All the pictures are gone, but the book is still here. He talks about all the energy and where it comes from, and how science has talked about it and how much there is, and then we get back to he mentions his valve-like detector. If you know anything about radio detectors and vacuum tubes, basically, you know, the detector is the thing that picks up the radio waves. Like if you had a radio and you were picking up a broadcast signal, that would be called a detector, you know. And then something I'm going to get to is he had semiconductor materials in there. He even had some radioactive stuff in there. And yeah, he was ahead of his time for sure. So let me get down to patents. Sea of Energy, what's the Tesla? He's talking about Tesla now. So if you get past all that, reactions by means of electron excitation, and this is where he starts describing, chapter 8 here, how he believed his device worked. And I'm going to say right now, he didn't know how it worked. He believed that he was somehow creating a resonance at a frequency above light, and up into the radiant energy spectrum, which is just impossible. You know, it's impossible. There's no way in hell that he had any resonant device that worked that fast. It just, you know, the fastest they could make back then was like 10 megahertz. I mean, they could only, their fastest oscillator was like 10 megahertz. So he was wrong about where the energy came from, but I believe he did actually make it. And like I showed here, you know, the energy's there. You just got to know how to get it and utilize it and stuff, you know. And he does say the correct things in some of his writings. He says you got to make a siphon, and that's important. And I'm going to get to that here in a minute, once I get to explaining how a person needs to go about this. But first off, he starts talking about basically he's got a resonant, he's got a vacuum resonator, a vacuum tube that's an oscillator, and it has a activated catalyst on the electrodes, so it is making secondary emissions of electrons or charged particles. But that still isn't enough to get the frequency up as high as he was talking about. So basically he's got a resonator, and then the rest of it, if you read it and you try to understand what he's saying, the rest of it is just capacitor banks. Now these capacitor banks have what he calls valves. He always calls them valves. The valves are not rectifiers in the sense that they operate as radio valves in changing AC or HF to DC. So he's saying they're not rectifiers. The valves aren't rectifiers. He says they have an actual valve action in stopping the flow of energy, which may be thought of as oscillatory action similar to waves of the sea. Basically what he's saying is he basically made a valve that lets the overflow energy, you know, he's got this energy coming into all this capacitor banks, you know, vacuum capacitor banks, and he's got this special valve that he made that allows the excess energy to overflow and move on, and only in one direction. That's basically all he's trying to get at, but he don't know how to explain it right because he's so far ahead of his time, you know. So the excess energy is allowed to overflow and move on to the next stage, and that's basically all it is. And then and that's really all it is. He's got an oscillator circuit, and he's got a capacitor bank, and he's got a valve system on these capacitors, so you know, once they're full, they overflow and move on to the next spot. And you can read all this, and I suggest you do, and try to make sense of it. And this whole thing is a good read either way, you know. And he starts talking about resonance here. And here he says the amplitude of the oscillations until the peak pulses spill over into the next stage through a special detector and valve that prevents the return or feedback of the energy. So yeah, he's basically, you know, this is 1930s. They don't even have a diode yet. They don't have a transistor yet. So, okay, well, what did Thomas Moray invent? Well, this right here is in his patents. I know it's kind of hard to conceptualize this, but these things are pebbles. These are little rocks. One of these is germanium, which is what diodes are made out of. One of these is a radioactive substance that people think is uranium or something like that. And then he's got a press fit of this little pebble and a contact point. That's an old school way of making a diode. It's basically, if you look up cat whisker diode, that's what that is. So he's making a diode, and he's using several types of semiconductor materials, and he's using a radioactive substance in this weird first of its kind vacuum tube here, right? So what is this? Basically, he made a transistor. It's a special transistor, but he made a transistor, you know. This transistor is made to open once it reaches a certain voltage and only allow the flow to go one direction, just like a BJT transistor. And that's all it is. I mean, he may get some secondary emissions, a little extra electricity from the radioactive substance, but that's really what it is a transistor. So mystery solved on that. Now, so basically all it is an oscillator and some capacitor banks. And so how does it work? Well, first off, you see what he's saying. He says capture of energy by resonance. And now if we go back to what I was saying that there's virtually no amperage. There's voltage but no amperage. And then you remember I was saying you can't have resistance, because when there's a resistance, there's voltage drop. There's always voltage drop across the resistor, and if there's no amperage to take up that voltage drop, it will be the entire voltage that drops. You know, so if you just put a wire up there and a wire to the ground with a resistor on it, you would get 0 volts. And it would actually start out as 200 volts, but the resistance would just knock it all the way to nothing. Like it was never there in the first place. And you'd be like, well, scratching your head, well, how come there ain't nothing here? Well, the resistance ate it all up, right? So, this knowledge all gets y'all to my understanding, which I'm going to show you, or I'm going to explain to you. I haven't quite figured every last detail out, because I'm trying to switch over vacuum tube tech to modern day tech, and we're talking about high voltages, and I ordered some high voltage capacitors and stuff, and I'm going to do some tests eventually, but I got so many projects going on. But okay, so let me get to the heart of it all. Yeah, and there's more pages on Thomas Moray where he talks more. He talks about the electric siphon, and that's what you want to do. Is you want to see, he thinks he's making some faster than the speed of light oscillations, but he's wrong. He don't understand what's really going on, is what's happening. So here is the trick. Now remember, I said you cannot have resistance, because it'll just eat away all the voltage. Now I could make a little circuit to show you that, but you guys get the point. You know, you can't have resistance. So you got all this free voltage potential, but you can't use resistance to get it. So how do you get it? You use a capacitor. You take the capacitor to the ground, the earth ground, and then you take the other into the capacitor. Now you're going to want a high voltage capacitor, and you're also going to want a fairly small capacitor, because let's see, I was going to talk about stuff over here later, but let me kind of draw it out for you. So say you got this cable running on some posts, and then you just got the wire that comes down, and then you got your capacitor, right? And then you got it going to earth, and then you're taking everything from right here off of this capacitor. That's fine, but you also got to realize the question I was asking in the beginning is this whole cable here acting as half of a capacitor? That's one question, and I'm going to show you exactly why that matters here in just a second on the circuit simulator. But another question is, I see a lot of people kind of half-assed doing these tests on YouTube with this atmospheric, and they don't get much at all, right? And then you see what they do is that they'll put a stake in the ground, and then they'll connect to something up here, right? Well, you gotta think, this stake in the ground, it's almost like the equivalent of having a asymmetrical capacitor, because you got this huge part here. So you get this huge capacitor plate, and then you get this tiny little negative part of the capacitor. You know, instead of having to equal or close to equal capacitor plates, you know, you get this little tiny negative one that's just this tiny spike. And you got to realize that the dirt in the ground, that's actually a semiconductor. Some of it's not even conductive at all, and what is conductive is a semiconductor. So the dirt is not really... Is somebody knocking on my door? Oh well. The dirt is not really that conductive. So I think a lot of people's problems is they need to like dig a hole and put a bunch of metal underground and spread it out, or find another underground stream and connect into that. You know, basically get a better ground, and through the process of elimination you make sure that ain't your big problem, you know. And so yeah, I think just sticking a tiny stake in the ground a foot is not good enough, because the dirt is a semiconductor. It's not a really good conductor. So that's one point I was wanting to make. Now, where was I here? Oh, the trick to making it all happen. So I think, here's how I think it needs to be done, considering modern stuff. Hold on, I think somebody's at my door. No, ain't nobody at my door. I'm just hearing shit. Alright, so okay, you got two capacitors. Alright, we'll just say this is the source, this is the ground, this is the atmospheric air. Oh shit. And all this resistance here is going to be represent how little current is actually there. So we're going to crank this one up to 1 gigaohm, and we'll leave this one at 1K. And give me 1 second to check the door, guys. Sorry about that. I guess some people are outside talking, and I thought there was people at my door wanting in. Okay, so yeah, you got this huge amount of resistance that represents how low the amperage is, and we're going to turn this voltage up to, like, we'll just say 300. And then so this is the ground, and this is our main capacitor, right? And then this is going to go up to here. And say we want our main capacitor to be a little bigger. I got these 2.2 UF capacitors that are good for 400 volts, which is not good enough, but that's what I got laying around, so I'm going to act like we're doing it. So what if we were to watch this voltage, and I'll show you this thing later. Gotta take that off of there to do this. So look at this. We got well, that's not accurate because that's not accurate because this amperage is so low. This capacitor here in real life would take a really long time to fully charge up. It would take I think I did some testing and it would take like 30 seconds or something really long, you know, for a 2.2 UF at 300 volts. So this is going to take really long to charge, but I propose that we take a fairly big one like this and stick it as the main one. Let it sit there long enough to get all fully charged up, and then we take our other one, I would say like a whole bank of really small ones, like in the in the picofarads. So let's see. Say like 20 picofarads. And then just have a whole bank of these. You know, just consider this a bank of 20 picofarads. And they're all connected off of this, right? So, now the whole point of how do you make a siphon is, here, let me cut this off and show you what I was initially going to show here. Obviously, this is a resonant circuit. A resonant circuit has a capacitor, some resistance, and an inductor. So, I'm not sure which side this thing is. So we got the resonant circuit going. Let me get rid of this orange. Now this frequency generator here, it's got an amplitude of 5 volts, right? So it's only putting out 5 volts into this tank circuit. And you can see it's maxed out at 5 volts, but it's not at its resonant frequency. So if we turn it up to its resonant frequency, which is 20.5 kilohertz, look what's happening. We're only putting in 5 volts AC, but it's running up to 63 volts AC. So it's a little more than 10 times the voltage that's put in is being put out. You know, and you got and some people might think, well, I mean, that's resonance, you know, that's how a boost converter works, you know, or any kind of switching power supply. But you know, this ain't free energy. That just means it's sucking more amperage out of the source. And the reason it's doing that is once you hit the resonant frequency and you're closer to the resonant frequency, the reactance and the resistance disappear. And basically the inertia of movement overrides the resistance and the reactance. Well, I mean, when it's AC, you call it reactance, but it's resistance, you know, resistors, resistance. So what happens is when you hit the resonant frequency, it overrides what resistance is in the series. And it also can create a negative resistance. And that's why it's almost 10 times the voltage that's put in, because all the resistance disappeared. And like I said, you know, voltage drops over a resistor. So that's the trick we're going to use to get this to create a siphon and pull this electricity out of the air. Is we're going to use the negative resistance of a resonant circuit, which is exactly what Thomas Moray did. He just, I don't know why he didn't quite understand what was happening. So we're going to take our resonant circuit. So we're going to take an inductor, a capacitor, and then we're going to take a phase lock loop, which is a phase comparator with a voltage controlled oscillator, and you get those phase lock loop chips. I got several of them. They're really fun to mess with. And what the phase lock loop will do is it will trigger something at the correct timing of our tank circuit. So what we're going to do, if I get rid of all this, get rid of that, get rid of that. So here's our antenna up in the air right here, right? And it's coming down to our main capacitor, which is a fairly big one that took a while to fill up, you know. And then we got a bank of small ones, and these small capacitors sticking off the side here, you know, if they were all drawn at once, you don't want them to completely empty this big capacitor. I mean, you might want it at like 3/4 or a half amount, you know. And the thing is, you know, this antenna that you got up here, depending on how big your antenna is, you know, you could draw power, a tiny amount of power, super quickly. You know, like in the megahertz, you're dumping this 20 picofarad capacitor in the megahertz frequency. And because it's such a small amount and you got a nice big antenna, is refilling it just as quick as you're taking it. So, you know, this is like your reserve tank here, and this is getting refilled as fast as you can take it, you know. So you want a high frequency, I would say, you know, 100 kilohertz or better oscillator circuit. So we get our oscillator circuit, and what we want to do is we want to discharge this bank of tiny capacitors, and that's kind of a problem, you know. I mean, Marais did it with vacuum tubes, and vacuum tubes are kind of totally different. Ah, crap. Oh, we just lost everything. But basically you gotta put a transistor in there. So that means you gotta have enough capacitance of the tiny capacitors, the bank of tiny capacitors. You gotta have enough capacitance there to actually make this transistor work, you know, at least in the beginning, you know. So you know, you got picofarads going on, but you got to have enough picofarad capacitors. I mean, these should be picofarads, you know, and you've got to have enough of these to where their capacitance adds up to enough to just make the transistor work, you know. So now when this transistor works, we're going to have, okay, here's our main capacitor, here's our source. We're not going to mess with the resistors, just know that there's very tiny amount of current. So you got this whole bank of, you know, tiny picofarad capacitors, and they're all connected together in the same way. And but here's the, okay, you know, I'm kind of going around in circles here, but here's the trick. You know, you got to take a transistor or a MOSFET, or a vacuum triode thingy. You know, I'm not super into the vacuum stuff. But whatever you do, you gotta take your phase lock loop system, and so this is gonna represent our phase lock loop. We'll make it a pulse with a, you know, like a 5, you know, whatever, to run our MOSFET or our transistor. So this is our phase lock loop, and then we got our tank circuit, and our, like, you know, maybe a Colpitts oscillator, but anything that doesn't have resistance. Resistance is your worst nightmare, and just this the voltage drop across this diode in the transistor is going to be an issue to worry about. Actually, I was thinking about using a thyristor, SRC thyristor instead of a transistor, and that way, and then just have this, and just have the, you know, it'd take more tuning to do it this way, but have the thyristor set up with in such a way to where when this capacitor bank gets to the full voltage or close to the full voltage, that the thyristor dumps it once it's close to the right voltage, dumps it into this tank circuit. Or if you have your phase lock loop, either way, you know, and you're just controlling when to dump these capacitors into the tank circuit to keep the tank circuit in perfect resonance, because the whole point is that you want this tank circuit to be in perfect resonance and create negative resistance, and that negative resistance you want to go through your switching device, and you want that negative resistance to go through your capacitor bank, and you want that negative resistance to go all the way back up through the system and create negative resistance all the way to the source. And then you will have effectively made a siphon. And all this, you know, how I was saying the voltage drop, and you know, because the resistance, that voltage turns to nothing, and to where you didn't even know it existed in the first place. Well, all you got to do is supply, you know, take some AA batteries and get a resonant circuit going, get the negative resistance going all the way up through the system to the source, you know, back up through it. And then once that's going, then you've created your siphon on the static electricity. And really, to utilize the static electricity, because it doesn't have any current, you've got to fill up capacitors. You want to fill up capacitors and then move that to a bigger capacitor or whatever, you know. And you want to just keep filling capacitors until you've got enough accumulated that you can do stuff with, you know, like so once you got so once these are full, these capacitors are full, they dump into this resonant circuit, and once this resonant circuit, or I mean, either way, so you got some bigger reserve capacitors where it eventually gets dumped into, and once these reserve capacitors get to a certain point, then they can be you know, discharged through a transformer or whatever you're going to do to make them usable. But the main goal is to take all this free voltage potential and stuff it into capacitors, and you know, And like I said, when you're filling this big capacitor, your first initial big capacitor, and I said it would take like 30 seconds to even fill the damn thing. Well, if you've got negative resistance going from your resonance circuit, that will all change. You know, the capacitors will fill even quicker. So the resonance creates the negative resistance, and the negative resistance creates the siphon effect that is the electric siphon. And that's what it's all about, you know, creating a negative resistance and filling capacitors as fast as you, and with as much as you can, and doing everything with no resistance. And that's the trick. You got to use the resonant circuit. Alright guys, I guess I talked about this. I hope you understand what I was saying, and I hope I didn't just waste your time talking in circles too much, but you know, I had to try to get it out in a way that I thought everybody could understand. So it's all about creating a resonant circuit and using the negative resistance of the resonant circuit to create a siphon on the static electricity and stuff it into capacitors to accumulate it as fast as you can so it's actually usable. So I guess that's it. And like I said, you know, you want to have a better ground than just sticking a stake in there. I actually have an old well, and I was going to try to use that as the ground by throwing the wire with a chunk of metal attached down in the well, and I think that might do better. And like I said, oh, that's one more thing I gotta show you real quick. Remember I was saying I don't know if that cable in the air is actually considered half a capacitor or not. Well, if it is, then you got this problem. Oh, and I've got one more trick to show you to help you. If you really are interested in this, I got one more thing that'll help you. So if you consider this top half of this capacitor as your antenna in the air, and this bottom half of this capacitor, the bottom half of the capacitor you can consider as your antenna in the air with its insulator, and the top half of this capacitor you can consider as the air with the charged ions in it. You know, and if that's the case, then electrically it'll look like this, and then you've got the issue of dealing with the circuit in such a way to where this is considered a capacitor, and you gotta deal with it like it's a capacitor. So you know, you gotta realize that. I don't know how that wire actually shows itself. But now here's another thing. Remember I said you can't use resistance because you'll make everything just disappear? Well, you know, once you get everything started and you got a resonant circuit going, then and the negative resistance going, then it doesn't matter. But to get everything going in the first place, you know, everybody's used to voltage dividers with resistors, you know. But you can do the same thing with capacitors, and I don't think a lot of people really know that, you know. Oh man, I got too much crap going on over here. Either way, yeah, you put capacitors like this, and if I was to test here would be a third, here would be 2/3, and here would be the full voltage. So you know, just putting the same value capacitors like that, you are dividing the voltage, and you're doing it without putting a real resistance, a DC resistance in the system. So that's your little trick to like you know, if you got your phase lock loop, or your triggered thyristor to dump, and you know you're dealing with these high voltages and you don't know how to get your digital stuff to work with it without adding resistance that screws everything up, you gotta use capacitor voltage dividers. So alright, I'm gonna cut this video off. Man, I talked about this for a long time. Hopefully somebody gets something out of this. Eventually I'm gonna do some testing, but I got too much stuff to do for a couple weeks. Alright guys, later.